Today we're going to be talking about a vector function, and I just want to give a visualization for this because I feel like it may be a little hard to see if you're first going in to Calculus 3. So let's just take the vector function of r as or t as a function of this vector r is given as this vector here of t. So basically, let me increase my line size. X is going to be equal to t. So for every shift in the t value, so t of 1 is going to output x. T value of 2 is going to output 2x. You get the point? So y is going to be a square of t, and z is going to equal t to the third. Okay. Notice here none of the values can be negative, so t must be greater than or equal to 0. Okay, so to visualize what's going on here, we're going to first identify a surface, because you've probably learned that vector functions are going to lie on a surface in 3D. For this one, we're going to figure out it's going to be a cylinder, a parabola on the xy plane shifted among the z. So, and you can just do this by substituting x equals t into y equals t squared. So to make t squared, we're going to square both sides of this. This is going to become x squared equals t squared. Plug it in here, okay, and that's going to give us, I'm going to write this in red, y equals x squared. In 3D, this is going to look like this. So we have the x, the y, and the z. Basically what this is going to look like is it's going to look like, first, if we draw just a trace of it, it's going to look like a parabola, but that's going to be directed along the z-axis. Okay. So hopefully you can kind of see my attempt at a cylinder here. Okay. So basically we have this cylinder, and this curve, right, because vector functions describe curves in 3D, this vector is going to lie somewhere in this cylinder, right? It's going to be directly on it. Where I'm going to show you a visualization. I'm just going through the math right now, but you can see we have a cylinder, and somewhere that curve is going to fit on that cylinder somewhere. And the best way to find this function is to solve all your variables for t and set them equal to each other. To do this, like this, y would become the square root of t. So t equals the square root of y. And here it'd be the cube root of z is equal to t. And you can set them all equal to each other. So just to show you, x equals t, y to the 1/2 equals t, and then z to the 1/3 equals t. Okay, now I can just set all of them equal to each other because they're all commonly equal to t, just t, nothing else. So our line is going to follow this pattern. X equals y to the 1/2 equals z to the 1/3. Notice how this is true. Okay, I just want you to make sure that it's pretty solid that this is true. There's a rule in lectures. Don't use yellow. Yellow is a bad color to use, guys. And we're gonna see how this fits. So using this function, or not really a function, this curve, right, we're gonna fit it onto the cylinder. And to do this, I put it into Desmos, right? Beautiful Desmos. Okay, so hopefully you can see what I have here. And all I'm going to do, I'm going to come over a little bit. I have that parabola. Now, hopefully you can see it's a parabola, pretty straightforward. Remember, y equals x squared. That's exactly what I have here, but I have it shifted along the z. So for every, there's no z component to it, but every time we increase in z, this function is going to stay constant. All right, now what happens if we disable that and we draw in what we said, x equals y to the 1/2 equals z to the 1/2? Well, it's going to look like this, and it's a line that we found. So using our vector idea, we find that just from a top-down view, it looks like if we're not including any z component, it is x equal or y equals x squared, right, on just one side though. Alrighty, but then if we look down, we see that, okay, there's some z component, but it's a third. It's kind of interesting to see. It's going to increase that z by a third factor. So, it's hard to explain, but it's a cube factor instead of a square factor or just a linear factor. It's a cube amount that we're going, and what we're going to notice is that it perfectly follows on the sheet. Like, isn't that kind of fascinating? It just follows it perfectly, no matter how much we zoom out. That line is always going to follow that parabola. So just something interesting, a good visualization. So when your teacher is going to explain this as this line is going to follow our curve, that's what they mean. So hopefully you guys enjoyed. Thank you.